Honestly, most Paper 1 pharmaceutical chemistry, pharmacology, physiology, and pathophysiology study guides teach this stuff backwards. Here's what they keep getting wrong, and what to do instead. We're going to look at the structural secrets of drugs, the physiological loops that confuse everyone, and the specific traps examiners set for the unwary. Let's get into it. You've seen the textbooks. They're dense, dry, and frankly, they miss the point of how these subjects actually connect. I want to show you the logic beneath the surface that makes the hard questions feel easy. Okay, new topic. Between you and me, the chemistry section isn't about drawing perfect hexagons, it's about predicting where the electrons want to go before the drug even hits the receptor. Section, good. Let me put it another way. Imagine a patient taking a pill that just sits there, refusing to move. If a drug is too lipophilic, it's like trying to dissolve a stick of butter in a glass of cold water. Students often get bogged down in the ring structures, but the secret is looking at the polar groups hanging off the edge. Why is the wrong answer so tempting? Because we gravitate toward the big, complex part of the molecule, but the tiny hydroxyl group is often what determines if the drug even reaches the bloodstream. What I see students do is ignore the salt form, which is actually where the solubility battle is won or lost. Think about trying to put your left hand into a right-handed glove. It might go in halfway, but it's never going to work the way it's supposed to. This is exactly how enantiomers behave in the body, where one version heals and the other might be toxic or just dead weight. The thing nobody tells you is that a racemic mixture is basically a 50% diluted dose of the active stuff, yet we often treat it as a single entity. I've seen so many candidates lose marks because they forgot that the inactive mirror image still has to be processed by the liver. Now, here's the thing about pH. Imagine a drug traveling from the highly acidic stomach into the neutral blood. It's like a person changing clothes for a different climate. If the drug becomes ionized, it's suddenly wearing a heavy coat that prevents it from crossing any membranes. We often debate whether a weak acid stays unionized in the stomach. The answer defines the entire absorption profile. What I've noticed is that people try to memorize the Henderson-Hasselbalch equation without realizing it's just a tug-of-war between the drug and its environment. Stay with me here because we're moving from the what of the molecule to the how of the effect. Picture a key in an ignition. A full agonist turns the key and starts the engine, while an antagonist just sits in the lock, blocking anyone else from starting the car. But what about partial agonists? They turn the key, but the engine just sputters. Students get tripped up here because they confuse affinity, how well the key fits, with efficacy, how well it turns. You can have a drug that binds tighter than anything else, but does absolutely nothing to the cell. That's the secret to understanding why some blockers are so hard to displace. Okay, buckle up. This next bit catches even experienced candidates. Imagine you're walking on a narrow bridge over a canyon. The therapeutic index is the width of that bridge. For some drugs, it's a wide highway. For others, like digoxin, it's a tightrope. Why is this a trap? Because the effective dose and the toxic dose can overlap in a way that makes standard dosing dangerous. Actually, let me back up. The real trick is realizing that the index isn't a fixed number. It changes based on the patient's renal function. Now here's the thing. Think of the liver as a factory floor. Induction is like hiring a night shift. Suddenly you're processing drug raw materials at double speed. Inhibition is like a strike. The machinery stops and the drug levels start piling up in the warehouse, which is the patient's blood. The thing nobody tells you is that induction takes days to kick in because you have to literally build more enzymes, but inhibition happens almost instantly. If you miss that timing difference on the exam, you'll miss the whole interaction. Right, quick reset. We need to talk about how the body fights back when we try to change it with medicine. But, Horse says. So, watch this. Imagine the body detects a drop in pressure like a leaky pipe in a basement. It doesn't just fix the leak, it panics and turns the water pressure up to maximum. This is the RAAS loop. It's a cascade where one signal triggers the next, eventually leading to salt retention and squeezed vessels. Students often struggle because there are so many A words. Angiotensin, aldosterone, ACE. If you remember nothing else from this section, remember THIS. The whole goal of this system is to keep the kidneys happy, even if it kills the heart. So, watch this. Think of the autonomic system as a seesaw. On one side, you have fight or flight, and on the other, rest and digest. Most people think they work independently, but they're constantly pushing against each other. If you block the parasympathetic side, the sympathetic side doesn't just stay the same, it wins by default. What I see students do is treat side effects as random lists, but they're just the seesaw tipping. Dry mouth isn't a random glitch, it's the inevitable result of blocking the digest side of the board. Visualize a row of dominoes. To start the fall, you need a specific amount of force. That's your threshold. Once it starts, there's no stopping it until they all fall. But here's the catch. You can't set them back up instantly. That's the refractory period. In the heart, if you mess with the timing of these dominoes, you get an arrhythmia. The thing nobody tells you is that most antiarrhythmic drugs actually cause arrhythmias if the timing is off by even a millisecond. It's the ultimate high-stakes game of cellular timing. Wow! Okay, final stretch. This is where we see if the drug actually leaves the body or stays long enough to cause trouble. Imagine a drug entering the body like a traveler passing through customs. The liver is the customs agent. For some drugs, the agent confiscates 90% of the goods before they ever reach the city. This is first-pass metabolism. Why do students miss this? They calculate the dose based on what's in the pill, not what survives the liver. The trick is knowing which drugs are liver-hungry. If you give those drugs intravenously, you're basically sneaking them in through the back door, bypassing the agent entirely. Right, quick note. Let's weigh two ideas here. Does a drug reach steady state faster if we give a massive loading dose, or is it purely a function of the half-life? Most people argue for the loading dose, thinking speed comes from volume. But the math tells a different story. Steady state is a time-bound constant. You can fill the bathtub faster, but the water level only stabilizes based on the speed of the drain. It always takes about 4 to 5 half-lives, no shortcuts. Understanding this prevents you from checking blood levels too early in a clinical scenario. Now, here's the thing. If you remember nothing else from this section, remember THIS. A prodrug is a sleeper agent. It's completely useless until the body's own enzymes activate it. We use this to cheat the system, to get drugs past the stomach acid or into the brain. But here's the danger. If a patient has a genetic variant or a liver condition, that sleeper agent never wakes up. You end up with zero therapeutic effect, and you're left wondering why the perfect drug isn't working. It's not a failure of the drug, it's a failure of the activation machinery. We've covered the structural logic of molecules, the seesaw of the autonomic system, and the timing of the liver's factory floor. Success on this exam isn't about memorizing lists, it's about predicting how these systems interact when you throw a drug into the mix. Next video, I'm tackling the section that trips up even the experienced candidates on the paper one: pharmaceutical chemistry, pharmacology, physiology, and pathophysiology. Subscribe so you don't miss it, and meanwhile, run a free practice test on pharmacycert.com to lock today's material in. Seriously, go see if you can spot these traps in a real test environment.